that any better? No echo? Ah, good. I figured it out. Sorry about that. So that's not quite class time yet, so we'll just wait for a minute or two here. You're welcome to turn on your camera, unmute yourself if you want, but it's totally up to you as we get started here. So you can Zoom how you want to Zoom. And I'll test my slide sharing in a second and all that stuff. If someone wants to unmute themselves and talk to me, I'll make sure that I can hear you. So.
Hello, it's Brianna.
Okay. All right, good. I can hear, so everyone's fine. And so, of course, this is going to be weird. And we are recording, I need to remind you, because this is a class and we have our World Campus colleagues that will either join us synchronously if they can, or they'll watch these asynchronously. So just as a disclosure, the Zoom is being recorded and it will be posted as a video that will be available to the members of the World Campus class. So that is a disclosure. If anyone's uncomfortable with that situation, just let me know and we can figure it out. Let's see. Okay, it is 1:35. Welcome to MATSE 556. Trying to figure out where to look because when I look at the camera, I can't see what's going on the screen. So anyway, welcome to MATSE 556. Now, this is an elective in the additive manufacturing and design sequence, or the 3D printing masters if you want, but it is a material science class. That's what MATSE means. And so we're really going to discuss the details of how polymers and composites, how their material characteristics influence additive manufacturing, the challenges of getting high fidelity 3D printing with these different materials, and how the material fundamentals, how the things that are intrinsic to polymers work in additive manufacturing. So how do thermal transitions or viscosity or viscoelasticity, how do all those polymer science concepts influence what happens in additive manufacturing? We will talk about additive manufacturing equipment. We will talk about additive manufacturing design and additive manufacturing applications. And so hopefully there will be something for everyone in there, but the theme of the course will always be materials and how those materials interact in the additive manufacturing ecosystem. We're not going to talk a lot about ceramics or metals because the course is about polymers and composites, but a composite could be a mixture of metals and polymers, or a composite could be a mixture of polymers and ceramics. And so we'll talk about composite science and how that's addressed in additive manufacturing of these types of polymers and composites. So if you have a question, just go ahead and raise your hand so I can call on you, and then you can unmute yourself and then go ahead and ask it. Or if you have like a question like, back on slide 5, I'm not getting it, just type it into the chat, and I'm going to try and keep an eye on both the lecture and the chat. I might miss something. And so, if I keep talking and talking, just raise your hand, I'll try and catch it. Or, if it's an emergency question that you need to ask, just go ahead and unmute yourself. It's no problem. Now, this is a mixed mode class. And so, because things, of course, are totally up in the air the first week or two, we're going to be online, and our room is only approved for 6 people, and that's 5 students and 1 instructor, and maybe we need a videographer. I need to figure that out. And so we will figure out as things change, or perhaps as they increase the occupancy of the room. So we're hoping that things go well and they'll let us have a few more people. We will have some in-person lectures if we're able to, but with all the unknowns, I wanted to start on Zoom. And I think most of you our graduate students. And the faculty is really focused on keeping our graduate students healthy so you can accomplish your graduate program, so you can spend time in the lab, so you can make progress on your advanced degrees. And so I encourage you to take that seriously, because if things change at Penn State, we are going to try and keep the labs open, and we're going to try and keep graduate students doing the research that they need to do. In the spring, we had to close down because we didn't know what was going on. But there's a lot of planning right now. No matter what happens to the undergraduate classes, we're going to try and really keep the graduate programs going, because we know people need to graduate. Companies are still interviewing. I mean, my students are still getting interviews, they're still getting jobs. And so we want to keep the graduate students moving. And in order to do that, we need to make sure that you all stay healthy and can accomplish what you need to do in the research lab. And I think because this is a graduate course and it's because an elective course, you know, we can do a lot of good things remotely here, but I'm always open to suggestions. Just shoot me an email. I'm happy to do one-on-one Zooms. You know, we can chat about whatever polymer additive stuff you want to talk about. I do a lot of additive research as well, and so we can shoot the breeze whenever you want. But we'll take the in-person part slow and steady so we can all make sure that we're ready to rock on research and that we keep the labs open. Okay, so again, this is recorded, and I'm going to try and share my screen here. I'm just going to share my screen. Okay. Well, that is what it is. But this is what I really want to show you. And so this is Canvas, of course. And so these links should work for the whole semester. So this was an announcement. If you didn't get the Canvas announcement, something might be goofed up with your Canvas, or you know, something's goofed up with your registration. And so just let me know if you can't get on Canvas and don't see these announcements. Of course, if you didn't get this, you can't find the notes, although I sent an Eli announcement too to make sure everyone was on the same page. So I'll send announcements as needed, but I won't send announcements for homework or things due, because you should be keeping an eye on what's going on in the assignments tab, and you've got 2 assignments ready to go. One is due next Monday and the other is due next Thursday. The one due next Monday will be easy. It'll take you 20 minutes. The one due next Thursday, let's just take a look at it. And there will be a lot of these. This is how the main work of the course is done, is that you'll find a paper, so a journal paper, using Google Scholar, Web of Science, SciFinder, whatever that is. If you don't know how to access those tools, just let me know. So I want you to find a scientific paper that deals with 3D printing of polymers or composites. So the requirements of the paper really need to describe the polymer that they used, whether it's PLA or Ultem or something like that, some information about the polymer, who made it, scientific names, etc., and the deposition method. And so this first paper, what you're going to do is you're going to find a 3D printing paper that talks about, we used this specific polymer with this specific additive manufacturing method. I don't want to see a paper from Penn State author, because I read all those papers anyway, so find someone outside of Penn State. And the paper should strive to connect details of the polymer to some interesting facet of the additive manufacturing technique or the final part. So I really want a materials focused paper. But of course, you all have your own interests. So some people might be interested in aerospace applications. Some people might be interested in consumer goods. Some people might be interested in metals. And so you'll have to find a polymer additive focused paper that has something to do with your interest, but that's up to you. I want you to highlight the major results of the paper and conclusions of the study and include a key figure where the figure really describes one of the main results so that we're all on the same page. Also, give me an indication of what you would do next. So if this was your study, what's the next step? How would you extend the study? What experiments would you do? What questions would you try and answer? What's good or bad about the paper? All papers have pros and cons. And what would you have done differently? So I want the citation of the paper in your reply. So title, authors, journal, year, et cetera, and then I want it to be at least 2 pages. Longer's okay. I've seen them, 5 pages, but I'm not going to make you do 5 pages. So just make sure it looks good. Make sure it's a couple pages long. It's all formatted up, and you can submit it on Canvas. Oh, hold on. I'm getting an email about Zoom. One sec. Let me make sure this is not the okay, I think we're good. This is not the great Zoom crash of the second day of class. Okay, so that's the homework. And so what I want you to do, and this is due next Thursday, so you have a week and a half, is you'll have to dig for a paper, find something that's interesting to you, and just upload it on Canvas. Let's start off the semester well. And the point of these assignments is that you're finding and reading papers that are interesting to your own interests. Graduate school is really what you make of it. You will have some assignments that you have to do, but you also want to do the work that helps you learn new things and helps you probe your interest, whether that's for your thesis or your final paper, or whether that's related to your job and these scientific papers help you. You want to make sure that you're reading papers that pique your interest. And so it will take some digging. It'll take, an hour or 2 to find the paper, and then a few hours to do the assignment. But that's homework number 2, due next Thursday. And homework number 1's easy. Just take a look at it and submit it. Let's see. The syllabus for the course is here. So whether you click home or syllabus, I think it brings you to this page, but I'm not an expert on Canvas. So if you can't find something, just shoot me an email. This is just a description, so you can check all that stuff out. Please email me anytime. Give me a call. That's not a problem. My office phone goes to my home phone, so don't worry about that. These are some of the topics. And then if you click on the syllabus here, we're mixed mode formally, and we will have in-person classes, and especially if things improve, we'll have a lot of in-person classes. So if someone is under visa pressure to have in-person classes or something like that, just let me know. I'm happy to do in-person. We just can't have everyone there, so we're going to need to figure out how many people we can have in the room at one time. The room is on the 4th floor of Steidel Building, 401. That's our conference room way upstairs. Everyone can get up there, but we'll have to see how things go in the next week or 2. Hopefully you are able to access the notes. That's one thing I didn't cover, but if you go, let me go back to the announcement. If you go to this box link, you should be able, the box link is right here. You should be able to find the notes and download them. And so you'll see the notes as I go through. You can download your own, take your own notes. You'll be able to see my annotations, etc. Again, if you have a question, just go ahead and raise your hand and I'll call on you because I'm trying to keep an eye on that. I don't see anything quite yet. Or shoot me something in the chat. Let me bring up the chat here so I can see it. Okay, I don't see anything so far. Let's see. Syllabus, course description, topics, details. If you haven't taken a polymer course, that's okay. You'll learn the polymer fundamentals that you need to learn in this class, but you'll have to be able to study the lingo and the nomenclature a little bit on your own. So what does molecular weight mean? What does amorphous mean? What does semicrystalline mean? So you will have to study the polymer basics a little bit, and I'll tell you what the major concepts are. Talk about composites, other interesting stuff. I should mention that we have a discussion group that you should see on Canvas, and so you can ask questions, drop in news items, stuff like that. That's for us to just chat about cool stuff in 3D printing. No required textbook. Reaction papers or response papers. There will be a final project. And then this is the grading percentage and the course grades. And so, you know, do a good job on that, but that's the syllabus. Any questions so far? All right. Feel free to jump in. I mean, I don't want this to be me talking for an hour and a half twice a week, or it's going to be a long semester. And so make sure that you just jump in there and ask questions if you have them. Okay, these are the notes, and these are on box, so you should be able to download these. If you can't download the notes are mostly in the form of PowerPoint slides, although there will be some readings and some PDFs that I'll put up. Question about office hours. Go ahead, Anna, unmute yourself and ask.
Yeah, I usually go by Paula. Yeah, I have a question regarding office hours. I saw it's upon request, but are you gonna like just assume like weekly times that you can like schedule for office hours, or is it more like we need to suggest a time?
Yeah, so if you want to talk on office hours, just send me an email with your availability. Because if I schedule a time for office hours, not everyone's going to be able to make that. You're graduate students, you have experiments. I don't know everyone's schedule. And there's not going to be like homework where you need to do like problems 1 through 30 and turn it in on Thursday. So we're not going to be working a lot of problems on office hours. It's more we're going to be talking about research papers, talking about, you know, details in the course. And so office hours will be more informal, like a discussion. And so when you email me and request an office hour, just say, I'm available at these 2 or 3 times. I'll pick one. I'll send you a separate Zoom link. And then if a couple people want to do office hours at the same time on the same topic, that's fine too. But there won't be a lot of group office hours where there's like 5 of us solving a problem. It's mostly going to be one-on-one chats about your interests.
Okay, sounds good. Thank you.
That makes sense? Yeah. Since it's an elective graduate course, you know, I'm not going to give you a lot of equation solving homework or things like that. You can do that in your reaction papers or in your final project if you want to do that, but this course is much more about discovering materials, discovering additive processes, and giving you the tools to really use those materials and additive processes in your research or in your job or in the future, if that makes sense. Okay, so I don't see any more questions. That worked out very well. Thank you very much, Paula. And so I'm just going to give you a little bit of intro on myself. Some of you know me. Some of you work in my research group, but a lot of you I'm just meeting for the first time today. And so my major interest in research is on membranes. And so membranes or electrolyte membranes are used in many different types of alternative energy conversion devices. And so I generally work in the area of alternative energy and polymer membranes for fuel cells. We have current projects going on in flow batteries. I've worked in areas like electrodialysis, and you can Google that if you don't know what it is. And even things like reverse osmosis, which is not necessarily an energy application, it's a water application, but it takes a lot of energy to do reverse osmosis. And so my background is in polymer science, but I generally work in these areas. And we've even 3D printed membranes that we've put in these different devices. And so you can check out my Google Scholar page if you want to know more about what I do in day-to-day research. So the main tool that I use is polymer synthesis. And so you will see some diagrams like this in this class. And so my degree's in polymer science. I worked in a polymer chemistry lab. I'm part of the polymer science community. So I really come at additive manufacturing through a polymer science lens. And the most important part of polymer science is knowing what the polymer is. And so you'll see some of this, perhaps if you're more oriented towards mechanical engineering, you'll see this chicken wire, or you'll see these stick figures of molecules. But my philosophy about learning additive is you need to know what the stick figures are, because that gives you some intuition as to how the polymer is going to behave. And I'll keep emphasizing this as we go forward. And that's why this elective is in material science and engineering. We focus on the materials and learn how they're applied in additive. So this is my tool. If anyone wants to talk about detailed chemistry, I'm happy to do that anytime. And there's some really nice additive papers out there from chemists that are starting to really use their chemistry knowledge in the additive space. And there's a lot of cool papers to read that are just coming out all the time. So as I said, we've made 3D printed membranes. You can go find the references on my Google Scholar, and this is really interesting. We're still doing this, and now we're applying 3D printed membranes in terms of making hydrogen production through electrolysis. And so I have graduate students and postdocs working on this in my lab right now, or on Thursday, Friday, Saturday, Sunday when our lab hours are. So this is really interesting. This has been a breakthrough in my group, because every single membrane that we ever made for 10 years looked like this. It was a flat sheet of polymer that wasn't very interesting at all. But now with additive manufacturing or 3D printing, we can really get some cool shapes that we could never get before. And so these are made using photopolymerization. And so we'll talk about what photopolymerization is and what it means for this course in the stereolithography unit, but this is coming up. And now that we have cool membrane shapes, we can also get other cool membrane functions like color change. And so this is a membrane that changes depending on the pH of the water that it's filtering. So now you can have a membrane filter that also reports to you through a colorimetric response if the water is contaminated or not. Like if you have an arsenic sensor in the membrane, or if you have a polymer that detects lead and changes color. Not only can you get fresh water out of this membrane or purified water out of this membrane, you can have the membrane tell you what's actually in the water in the first place. So that's a cool thing we've been working on lately. So if you're familiar with stereolithography and photopolymers, you know that you can produce things like this relatively easily. So these are all small demonstration parts that are on the order of, you know, a few inches on a side. But these, again, are photopolymers made using a Formlabs or another type of stereolithography or digital light projection printer. And so again, we'll talk about photopolymers and we'll get more into it as we go. But you can imagine how difficult it would be to make these shapes by hand in the lab. I mean, how do you do this? And so you can't even mold or injection mold some of these shapes with all the internal features. And so additive manufacturing has really changed how shaping of polymers has been done, both in research and in production. And we'll look at some of those production examples. And so additive is just not some researchy thing in polymers that you can go in and demonstrate some plastic toys, but it's being used in hearing aids. It's being used in shoes. It's being used in car components. And we'll look at some case studies of where additive is really making a difference in industrial manufacturing. So whether you're on the research side of things and you want to do something new and cool with additive, or whether you're on the industrial side of things where you're looking to deploy additive in your company or in the types of processes or products that you're interested in, there will be something for you in polymer and composite additive. Then it goes on from there. There's custom formulated resins, there's ceramics. So we will talk a little bit about polymer ceramic composites. If anyone's ever bought an SLA resin from Formlabs or EnvisionTech, they make what's called a ceramic resin. And all a ceramic resin is, it's a mixture of photopolymer and ceramic particles. So it is a composite. You know, this little tablet that I think Lachlan Peak printed in my lab, or maybe Kenny, is a ceramic polymer composite. So this already is a composite, same with this lattice structure, same with this glazed ceramic right here. And so there's a lot of ceramic science, there's a lot of colloidal science. You have to modify both the polymer and the ceramic particle in order to get this to work. And so right away, for off-the-shelf things, you have issues of composites that you have to deal with if you want to make these SLA type ceramics. We'll talk a little bit about filaments if you're interested in filaments, or if you read Jennifer Lewis's work. And if you are really stuck on ever finding a paper, I will refer you to Professor Lewis. And so let me write down her name so you know who she is. So you can Google her. She's probably the most famous 3D printing scientist, other than Chuck Hull, in the world. And so she does cutting edge research, and she mostly uses direct ink writing, although she's done some other things. And so if you really can't find a paper that you like, just look up Professor Lewis's Google Scholar, and there will be plenty of interesting things there to talk about. What's cool about Professor Lewis is that she started as a ceramist. She actually knows Professor Gary Messing very well. They worked in the same field, and Professor Messing, who just retired from Penn State, is a hardcore ceramics processing person. And so Professor Lewis approaches additive from the ceramics processing point of view, just like I approach additive from a polymer processing point of view. And I think you'll see a lot of impact that people have had that weren't necessarily trained in additive, using their skills as materials experts to influence additive research and additive production. And so additive manufacturing is just not for electrical engineers and mechanical engineers, although there's a lot to do in that area as well. It's really for material scientists and people who are interested in processing. They can have a lot of impact in additive as well. Here's some nice pictures. You can take a look at that. You can look at this picture right here. This is from Professor Lewis. This is a composite. And we can tell it's a composite because it has filler fibers in it. And so what's cool about this picture is that you see these are unoriented filler. So the filler is anisotropic, which means it has an aspect ratio. So these are filler fibers that are anisotropic. And then once they come out of the filament, so this is a direct ink writing filament. sometimes called a road, and we'll talk about that. But you see now these are oriented fibers in the filament. So you go from an unoriented filler to an oriented filler in road. And that's because you have to squeeze the material through this orifice. And this orifice is going to be on the order of 300 microns or something like that. And so as you squeeze a fluid through that small opening, the fibers can't fit in sideways, and so they have to orient. And so now you get really different material properties in the extruded road than you get from having some unoriented isotropic mixture. Now, that's a lot of nomenclature. That's a lot of vocab words. If you don't understand a vocab word, just shoot it up in the chat. Just say, I don't know what a road is, or I don't know what a filler is, or what does anisotropic mean? Because these are the type of technical words that we're going to use in a graduate course to really describe what's going on. And we'll talk about degree of orientation. We'll talk about shear rate. We'll talk about why things are oriented. But if you're uncertain as to what the vocabulary is, it's going to be hard to follow the discussion. And so I know not everyone here has had all the material science or all the polymer science courses. And so it's fine to ask questions or ask questions in the discussion group on Canvas, you know, whatever you think. And if it's going too fast and if it's too much jargon, just stop me and back me up. That's no problem. All right, so this is just more data, you know, so you take a qualitative picture, so you'll see a lot of pictures of parts, but of course we're scientists and engineers, so we need data. And so this is print speed, and since this is a velocity, this is in linear centimeters per second. So this is basically the road extrusion velocity. And now this pressure is the pressure here. So to extrude this thing, you're going to have pressure. And so as you increase the pressure, you increase the flow rate, and you can increase the velocity. So this is called the extrusion pressure. And in this case, we get a relatively linear relationship between the extrusion speed and the pressure. We just drew some straight lines through this with certainly some noise or error bars because the speed is so low. And so it doesn't have to be a linear relationship. We can look at the fluid dynamics. If you've studied fluids before, you know that there's a velocity field in this nozzle. And so we'll talk about some of that and some of the ramifications for the relationship between the material characteristics, how it extrudes, and then why that matters for printing. We'll look at finished parts. So this is just an example of an electrically conductive part because we're measuring the potential or voltage versus the current. So this is an IV measurement. This is a semiconductor because it has that S shape. But now this is a composite part between, this one's carbon black plus polymer. And so we call this the microstructure of the composite. What does it look like on the microscopic level? And of course, we have the macrostructure or the shape, which is controlled by the printer. And so we're not going to talk a lot about slicing G-code, printer control algorithms, details of the electrical, mechanical, and software components of 3D printing. I think other courses in AMD cover that. We are going to talk about the shape because the process that we pick, whether it's direct ink writing or fused filament fabrication or stereolithography, determines our shape fidelity and the types of shapes that we can make. And the printing process really dictates the types of materials we can use. And so we're going to talk about the connection between material, printing technique, shape, and then we're going to talk a lot about material characteristics and how those material characteristics in additive are perhaps different than the material characteristics in conventional polymer processing. So if you want to learn how to do slicing, and if you want to learn how to build printers and stuff like that, there are other courses for that. This is really going to focus again on the materials issues, all the way from chemical structure to microstructure to shape and its relationship to process. Okay, and we're in Steidl building. If you haven't seen Steidl building or haven't seen the labs, you will be welcome eventually to come and take a tour of what's going on in there. This is a picture when our Arkema 3D printing lab was empty. Now it's very full. And an old picture of my research group before the building was renovated. But please, if you're interested in additive research or you just want to talk about polymers or materials research in general, please reach out. I'd be happy to chat about that. Okay, are there any questions before we start getting into the meat of the lecture here? Anything people want to bring up? Anything people are confused about? Can't see the notes? Can't get on Zoom? Can't see Canvas? All right, I have sent out bad links before, so you know that's feel free to raise that issue. Or I've missed emails before, and so you know I'm sometimes not available like for office hours in the next hour. But you know, if you remind me once or twice, especially if you send me a Canvas email, because I see all the Canvas emails directly, just shoot me an email. I'd be glad to sort out any problems. And if things come up, if you can't attend class, if there's urgent research or job issues, or one year I had someone who was deployed on a Navy ship installing a 3D printer, so he was unavailable for 2 weeks, you know, that's fine. Since this is a grad class, there will be a lot of flexibility in terms of how we conduct the lecture. So just give me a heads up on what's going on. I'd be happy to work out whatever we can work out. That's no problem. Okay, so I'm going to talk a little bit about technical details of polymers, and we're going to have a lecture or 3/4 of a lecture warming up what are polymers, how do they work, what are some of the material science of polymers, and this is really so you can understand the characteristics of polymers that you should care about when you go to additive, because you know, polymers behave differently than metals. So of course, the finished components are different. You know, we can recognize a piece of steel versus a piece of polymer, but the characteristics of the material also really influence their processing. So you don't cold roll polymers very often, or you don't injection mold metals except under special powder metallurgy conditions. And so the types of processes that we're going to talk about are really dictated by the material characteristics. And so we need to understand those material characteristics in order to understand the processes. So if you don't know what extrusion is, or you don't know what injection molding is, you're going to have to look at some online resources to figure that out. I will talk about those things, but I'm not going to teach you about injection molding very much, or I'm not going to teach you about twin screw extrusion. I'm going to mention those vocab words, and I'll expect that you either ask questions when you don't know what they are, or you're able to find some of that information on your own, because that's the baseline for understanding polymers, and we build on that baseline to understand polymers and composites in additive. Okay, I don't see any questions or raised hands, I don't think. I still see some people moving on the Zoom, so I assume you're mostly there with me. And we'll go until, I think the class goes until 2:50, and so we'll try and go right on the dot because it's being recorded. And then we'll pick it up on Thursday. So polymers are different from other materials in a lot of ways. Now, if you know a vocab word about polymers that are different than other materials, you're welcome to put that up in the chat. So what are some characteristics of polymers that don't exist in ceramics, metals, semiconductors? Does anyone have any ideas?
They have glass transition temperatures and melt temperatures.
Perfect. TG, TM, great. What else? Anything about their flow characteristics? Go ahead.
Their viscosities can range depending
Yeah.
on what state they're in, raw or cured.
Great. So let me just wrap up viscosity as saying they're viscoelastic. Sometimes that has a hyphen, sometimes that doesn't, but that means that, and they also have a large range of viscosities. So just like in the previous diagram I showed you, that viscosity is really going to matter for extrusion out of that 300 micron orifice. And so it turns out that the viscosity of a molten polymer is about 3 orders of magnitude higher than the viscosity of molten iron. And so that's really going to influence the processing or the shaping of the polymer for sure. What else?
Capable of being cured or processed at different wavelengths, which is kind of a loaded statement because you can change your initiator package to do that, but some some kinetics go faster or slower depending on molecular weight of that, which goes back to viscosity.
Well, let's just put that down as we can do a range of chemistries, and that those chemistries can be fast, slow, slow, or they can be tuned. And so you can tune the chemistry to match the processing speed that you want. And certainly we do chemistry when we do ceramic processing, Oswald ripening, nucleation and growth, that can be chemistry driven. We don't do a lot of metal chemistry, although we make some alloys as we process metals. But this idea of chemistry as a knob or chemistry as a tuning parameter, whether it's in photopolymers or whether it's on another platform like a thermally cured epoxy, is something that we have to take into account for polymers for sure. What's another chemical process of polymers that's less desirable? Degradation. What's a maximum temperature that polymers survive at? Does anyone know? Thousand C, 1500 C, 400 C, 100 C. What, when I say polymer, what sort of number goes in your head? Maybe 400 C max. You know, if you take a polymer and you heat it up in air to 400 C, it's going to start degrading. And of course, lots of ceramics don't even know that it's 400 C. They don't care. Lots of metals don't care either. And so the processing temperature or the window for processing polymers that you have is a lot of times smaller than you have for other materials. And so we need to keep an eye on degradation because it can happen quickly during processing. It can happen during additive. And so that needs to be taken into account when we start to develop additive schemes for polymers because they degrade differently, and degradation is just a chemical process. But that's a big consideration as we start to do additive. Anything else?
Thermal expansion coefficients can vary based on what polymers you're using.
Yep, you can vary CTE, modulus, toughness. Etc. I mean, lots of materials classes have a range of materials properties, but you can go from elastomers like silicone all the way to glassy polymers like PEEK. And so you have like 5 orders of magnitude range in some properties with polymers. And finally, I just want to mention on this slide that polymers are really unique compared to other materials because they are long chains. And that long chain nature of polymers is really important because that determines the viscoelastic nature of polymers. That determines some of the degradation behavior or mechanical degradation, because you can shear polymers enough or process them enough that you can actually break the chains. And so we need to think about both the chemical structure, so what does the chicken wire look like, but also how long the chains are, and that's really defined by the molecular weight. That is molecular weight is a fundamental parameter of polymers that we always need to keep our eye on, because a lot of the things that we wrote down on this slide are determined by molecular weight and then chemical structure. So if you're able to find information on molecular weight and chemical structure, you know an awful lot about the polymer before you even start measuring properties. Anything else people want to cover on this slide, or any questions people have in terms of special things about polymers that we need to keep our eyes on as we go into the world of additive?
I guess.
Yeah, sorry.
Go ahead.
Oh yeah, I just want to mention that there's that thermoplastic like kind of polymer where you can actually reprocess the material, like
Yep,
even after it's formed.
We'll talk about thermoplastics and thermosets. And so, like metals, of course, thermoplastics, you can melt them down and reshape them. But thermosets are like ceramics. You have to grind them up and you can't reform them. So we'll definitely talk about that.
It's funny we both went at the same time because that was my comment as well. Thermoplastic
Great.
versus thermoset.
Yeah, so and those characteristics of polymers really play into the additive manufacturing scheme that we're going to pick. So whether we're trying to make a thermoset or whether we have a thermoplastic, there are certain types of thermoplastics that are more amenable to some processes than others. So we'll cover all of that for sure. But you definitely, with the chemical structure and the molecular weight, you really want to know what some of those other characteristics are as you think about polymers and additive. Great. So along the issue of molecular weight, and this is sort of the one esoteric slide about polymers that we have. Remember, polymers are one molecule wide, but they're many molecules long. And so if you've ever taken a polymer science class, you know what a monomer is. And so your monomer might be something like ethylene. That's a very small molecule, right? It's just 2 carbons big and a carbon and a hydrogen wide, so you can figure that out, but it's like just a couple of angstroms in each direction. And so this is ethylene. And the polymer that we make from this is called polyethylene. That makes sense. You want to get comfortable with this type of nomenclature so you know where the carbons and hydrogens are. But this N here is number of monomers. And so does anyone have a molecular weight in their head? Well, first of all, what's the molecular weight of ethylene? Anyone know?
28.
Yep, so we've got 12 times 2 is 24 plus 4, so this is 28 grams per mole. Does anyone have a molecular weight in their head for what polyethylene is, or the molecular weight of a polymer in general? In order to make it over the bar to be a polymer, what does the molecular weight have to be?
Like 5,000 to 10,000.
So maybe 5,000 gram per mole. What's a top end? So that's maybe the very, very minimum, but what's the top end of molecular weight for polymer? Maybe 1 million grams per mole. That's pretty high, but there's ultra high molecular weight polyethylene that's 10 million grams per mole, we think. But 100,000 grams per mole is not out of the question. And so that's a lot of monomers of ethylene comparing 100,000 grams per mole versus 28 grams per mole. And so this tells you how big N is. And of course, N is related to the aspect ratio of the chain. Now chains are coiled up. We'll talk about what chains look like depending on how processing is, but this sets the stage for understanding the important part about polymers, which is the molecular weight that really feeds into the properties. I see a hand up. Eric, go ahead.
Sorry, I was scratching my head.
Oh, okay. Yeah.
My bad.
For some reason, I can't see all the, I can see all the participants now. So, Eric, if you just want to click your raise hand button again, your hand on Zoom will go away. That's the hand I saw.
Oh, where's that?
That is a very good question. I think if you go to participants, there you go. Went away. Yep. Okay. Yeah. You guys can figure that out. Yeah.
Sorry.
So
It was the other Eric. That was me.
Oh, sorry.
Sorry about
So, I see Eric Miller and Eric Jacobs now. So I'll try and be better with the names. It's actually going to be a lot easier to learn the names on Zoom because they're all sitting here versus in class. It takes me a couple of weeks. But anyway, if you do have a question that's not urgent, you can raise your hand on Zoom. You can click that icon and I'll call on you. Or again, the chat, just say, I have a question and I'll be able to call on you there. Okay, so again, we're going to talk about a couple esoteric things about polymers, but of course this is an additive course. And so we're going to talk a lot about additive, but if we don't understand polymers, it's really hard to understand the additive part. Okay, so what unique features of polymers do we have to think about for additive? And I'm just going to put down thermoset versus thermoplastic. Because that's already brought up, and that sets the stage for how we think about additive. So I'm just going to put that there as number one. But what other features of polymers do we need to think about now as we go to additive? Not just polymers in general, but if you're thinking about the various additive processes, which we're going to talk about on the next slide, what do we have to think about?
Miscibility within composites.
So sometimes we call that miscibility, sometimes we call that compatibilization. Sometimes we call that dispersion. But there needs to be some interaction, usually between the matrix polymer and the composite filler in order to make a stable composite. Otherwise, a ceramic powder and a polymer doesn't really want to mix, and you'll just wind up with a ceramic polymer that's sort of stuck in a polymer, and you don't get any composite effect from that. So that's a great one. So we have to think about that for sure. What else might we have to think about? Maybe processing time or processing time scale. Additive manufacturing is a dynamic process. Things are moving, conditions are changing, and so we're going to need to keep an eye on how fast the polymer is responding, whether that's chemistry or whether that's viscoelastic shear or whether it's shear thinning or shear thickening. And so the processing time scale and the time scale of changes of the polymer are going to have to be reconciled somehow as we start to think about additive processes and these characteristics of the materials. What else?
Maybe processing temperature.
Temperature. Temperature is a great processing variable. So if something's not working, the first thing you do is try and change the temperature because you don't have to change the material or the equipment. And so if you've ever worked in an extrusion processing building, or if you've made diapers like I have at Kimberly-Clark, or if you've made trash bags at New England Extrusion, the first thing everyone does is say, why don't you tweak the temperatures of the extruder just a little bit? And so temperature is the variable that we will use to adjust the characteristics of the polymer to get it to work in the additive process. And so we really want to understand both temperature of the process and any limits, and temperature response of the material, including thermal conductivities and things like that. So that's a good variable to think about when you think about what's going to be needed to additive polymers. Anything else?
Interaction with other materials, whether it's the build plate or another polymer you're trying to bond to in the process.
Yep, let's just do multi-material or material. Oh. Bonding, etc. That's a little bit different than miscibility or compatibilization or dispersion of the composite. But if we're going to make a product, lots of times it's just not one chunk of polymer or composite that we're going to use. It's a multi-material assembly. Excuse me, we're going to need a soft touch rubber plus a hard plastic, or we're going to need a hard plastic and we're going to need to bond it to a piece of glass or a piece of metal. And so we need to think about, in our additive process, we're not just making plastic toys or keychains or Pokemons or whatever. We're actually trying to make products that people are going to use. And I think if you pick up most things on your desk, it's going to be a multi-material assembly. And we need to consider that in additive. Anything else? That's a good one.
Viscosity.
All right. Well, oh, go ahead.
Or viscosity.
Yep. The viscosity comes back because that's always important, just like temperature and processing time scale. And so those are things that we'll talk about again and again because they're really driven by characteristics of the material. I'm just going to star a few things here because that is the fundamental part of the additive. And then to use our additive process in a product, of course, we need to think about all the other stuff that you'll hear about in some of the other additive classes as well. Good. So I think we're getting warmed up here on what polymers are and what additive is and how we're going to put those two things together in this class. And so you can start to think about what papers you might be interested in. You can start to think about Well, maybe I'm a materials person, so I want to focus more on materials. Or maybe I'm a hardcore additive person and I need to learn more about additive. Or I want to really design products, and so I need to learn about the different things I need to know about materials and processing in order to get the products that I want to get. And so I think, or at least I hope, there'll be something in this class for everybody, and there will be different facets that are easy or hard, or that you'll be able to relate to more or less, depending on what your interests are. And where you really develop your interests is through the papers that you'll read for your homework, and also through asking questions and guiding the discussion to the things you really want to talk about. Like if you really are interested in aerospace, you know, write papers on ULTEM, ask questions about continuous fiber composites, ask questions about low flammability polymers and other things like that. Or if you're really interested in shoes and elastomers, you can ask questions about how silicone or polyurethane might be used in additive. And so again, it's up to you to guide the class and to guide your own studying to your own interests. Okay. So in order to be on the same page in terms of additive, we're going to get on the same page in terms of polymers, but we want to talk about additive in a very succinct and standardized way. And so fortunately, we have ASTM, which tells us about standards. And so you'll see this in their ASTM document that's defined right here. So these are the people that define like ASTM standards for mechanical testing, or ASTM standard for measuring the coefficient of thermal expansion. Turns out they also have standards for processes. And so in the realm of additive manufacturing, which you'll see abbreviated AM, there's single step and multi-step AM processes. And within these types of processes, you can have fusion of similar materials or adhesion of dissimilar materials. The one interesting thing about this diagram, and this diagram is agreed upon by all the people that sit around the table at ASTM working groups and come up with these nomenclature and schemes, is that they lump composites just together. So you can adhere to similar materials, and composites is under there, or you have a single step process, but you still need adhesion of dissimilar materials to make your composite. And so if you follow the arrows, it's interesting where these wind up. And for some reason, they didn't put polymers in adhesion of dissimilar materials, although we know that sometimes you have to glue together two different polymers because polymers don't like to stick to one another. So there's advantages to diagrams like this, and there's disadvantages, but we need to understand it because this is how the world has decided to classify AM. And so when you read papers for your homework, there's no guarantee that the authors of those papers are going to use standard nomenclature. But I would urge you to use the nomenclature in the paper, or identify the nomenclature in the paper, and then in your own words, connect that to standard nomenclature. And so we'll talk about that as we go through. I will give you feedback on your papers, of course, because that's part of learning. You study and respond to some paper you're interested in. I give you some suggestions, and we go back and forth. That's great. That's how I assign you grades. But within a composite, there's this issue of material compatibility. There's issues of single step and multi-step. We won't talk a lot about multi-step, but you might want to read some papers on that you need to be aware of. And so this is just how we set up the field to talk about additive. Now, if we drill down a little deeper, this is one of the next figures in that ASTM document. They talk about AM of polymers. And this is where it gets interesting, because in order to additively manufacture something, really what we're doing is we're fusing material together in a very specific way to make a three-dimensional part. And so we're not going to talk, again, a lot about slicing or stacking up of layers and all that stuff. We will talk about that when we describe the processes. But if you're unsure as to why the fusion needs to happen for additive, go ahead and ask a question. We can talk about that. But really, there's two ways that we can fuse polymers together. We can do thermal bonding. I don't know why they call it thermal reaction bonding, but evidently the polymer expert at ASTM was out to lunch when they wrote this. Let's just call it thermal bonding, or usually this is going to be a thermoplastic versus chemical reaction bonding, and chemical reaction makes sense. And this is generally going to be a thermoset. So thermal bonding is like welding, and welding really happens when you have thermoplastics, although the welding of metals is not exactly the same as welding of polymers, but you can think about it that way. You heat up two polymers, you put them together, and you get them to interdiffuse and weld together. So that's generally what thermoplastics are. They are deformable under heat. Chemical reaction bonding is usually a thermoset because you have some cross-linking chemistry involved. And once you make covalent or strong cross-links in your material, you can't undo those very easily, and that's why they call it a thermoset. It's set and can't be reprocessed. So while this diagram is not perfect in the world of polymer science, it gives us a way to talk about these different additive manufacture schemes for processing polymers. Excuse me. Now, we should talk about material feedstock, which is the next level on the diagram. So if you've ever been in a MakerBot lab, you know about polymer filaments. We'll talk about those in terms of fused filament fabrication. And so we have the feed filament, and then sometimes we have the extruded filament or the road, but we're really talking about the feedstock here. So this is the polymer wire that you need for MakerBot and its like. We have melted material, and so sometimes we'll have a vat of molten polymer that we use. We can have polymer powder or polymer pellets, and we can also have polymer liquids that we use for chemical reaction bonding. And finally, we can have polymer sheets. So this is a unique one because this is going to be used in sheet lamination. And so we're not going to talk about sheet lamination a lot. It's an interesting curiosity. We're going to talk about one or two examples for composite. Sheet lamination, because there's some cool stuff out there, but we're going to de-emphasize sheet lamination. If you want to know what sheet lamination AM is, you can look it up, and you can write papers on it if you want. So that's just an interesting aside. Then we have our, well, what ASTM calls the material distribution, or this is how you take the feedstock from the level above and start to shape it into the additive structure that you want. So in fused filament fabrication of a thermoplastic, you're using a heated deposition nozzle to do melted material extrusion or thermoplastic processing, just like a MakerBot. If you have melted material, you might have a print head, and so you're gonna do multi-jet material printing, and we'll talk about what that is, and we'll describe all the different variations of what that could be. You could have powders, and so polymer powders are really interesting because you can do powder bed fusion, just like you do powder bed fusion of metals, if anyone has any experience with that. Although the melting and thermal characteristics of a polymer powder is much different than the melting and thermal characteristics of a metal powder, and so there's some distinct differences we need to talk about. Or you might have liquids in a print head and you're doing reactive curing and chemical reaction bonding. With liquid polymers, you can also do vat photopolymerization. That's very interesting. That's your typical SLA or DLP printing process, where now you're using UV curable thermosets in order to do the material shaping. So this diagram really sets up the framework that we want to use for the course. What are the characteristics of the polymer? What does the feedstock look like? How do we deposit that feedstock, or what's the additive technology? What's going on in terms of how that part's being built up? And then what's the ASTM nomenclature for the various additive process? So SLA, there's no such thing as a standard stereolithography process. It's called vat photopolymerization. There's no such thing as polyjet in ASTM nomenclature. It's all material jetting, where you're using light reactive photopolymer curing and you're spraying it out of a polyjet head. That's going to be material jetting. You have thermal material extrusion, so there is no such thing as fused filament fabrication in ASTM nomenclature. It's all thermal material extrusion AM. And so we just want to be clear as to what the fundamental processes are. There's 7 of them. That's generally how they're discussed. And how the feedstock characteristics and the polymer characteristics influence the parts that are built and the processing category. So I would encourage you to spend a little time with this diagram. Think about examples of each. Think about what you don't know what's going on. Like, I've never heard of sheet lamination, and put that in the discussion group on Canvas, and people will throw up some links to explain it to you. There's lots of awesome resources online. And so a lot of times in office hours, if you say, well, I'm not sure about this, I'll often say, well, did you just Google it and see what some of the 3D printing companies or the 3D printing communities out there have to say about this process? Because there's a lot of hobbyists out there. So there's some discussion boards of things that are interesting and also not interesting, because it is the internet. There's a lot of really good information, especially from companies like Ultimaker and Envision Tech and Stratasys. And there's some junk out there. Again, it is the internet, but it can orient you to the vast information out there in additive manufacturing and help you sift through things a little bit. And of course, papers in the literature, review papers, things on Google Scholar, things on SciFinder, the primary literature is always at least somewhat of a trusted source for finding information about AM. So I'm going to encourage you to do some of your own research and sort through some of this on your own to start to develop an understanding of the world of AM and how polymers and composites fit into that. I see a hand raised. Paula, go ahead.
Yeah, so based in this image that we have like all the way at the bottom, binder jetting, is this class gonna focus more as polymers used as like the materials being printed, or could it focus also on some stuff like binder jetting, in which it's not necessarily the polymer that's the material, but more of like helping like the particles of another material stick together?
So the answer is yes. What we're not going to talk about is the particles necessarily. So we're not going to talk about ceramic particles versus metal particles versus polymer particles and binder jetting, but we will talk about the polymer characteristics that you need to think about in order to glue those particles together. So what does the viscosity of the binder need to be? We're not going to talk about like dimensions of binder jetting. You can just look those up, what the characteristic tolerances are, or applications of binder jetting necessarily, although we're going to mention some of them. And so we won't delve into a specific process and its uses other than to talk about how polymers are used in that process. Does that make sense?
Yeah, that makes sense. Thank you.
Yeah, so in binder jetting, Paula is correct that you have a powder bed that you jet polymer into. We're going to talk a lot about that polymer or the binder in binder jet, and we're going to talk about less. We're going to talk less about the powder itself. Although with something like HP Jet Fusion, which is basically binder jetting, the binder is doing a lot of work in the material. And so we'll talk about HP Jet Fusion in detail and what's possible, because that's really driven up. Hold on, battery is low. Oh, that's just in my stylus. Hold on one sec. We're going to talk about the binder in HP Jet Fusion, because the binder is doing a lot of the work, and that's cool in terms of it's also related to this technology called high-speed sintering that there's been a lot of things done. But if you're interested in other aspects of binder jetting, I'll encourage you to find some papers to discuss in your reaction papers that really bring together all those ideas, and maybe discuss a couple different binders and why those binders are used, and then go on to make parts through binder jetting.
Okay, thank you.
You're welcome. Any other questions before we close? It's almost 2:50, and I'm going to try and keep exactly on time, so our videos work out. And anything else that people want to talk about before we close here? Okay, well, I will post this video again. If you're opposed to being on video, you can go without video on your Zoom. That's absolutely okay. But this is your notice that these videos will be available to our World Campus colleagues. And so I will see you on Thursday, same class time. If something is not working on Canvas, or you can't find the notes, or you can't find the homework, just shoot me an email. If you're concerned about class content or something, and you want to have an office hour, just let me know. Remember to give me a couple times for your availability, and then we'll get something on the calendar. So thank you very much. I will see you on Zoom on Thursday, and I will see you in person when we're able to get that done. And if you want things one way versus the other, feel free to let me know. Thank you. I hope everyone's doing well, and I will see you on Thursday.
Thank you.
Thank you.
Thank you.